Another Teardown Tuesday. You might notice things look a little different. That's because my my office has actually moved into one of the adjacent rooms. Sorry, I was connecting an ESD mat. So we now have the entire space we're working in previously dedicated to manufacturing and assembly. And now I've got a nice clean room for working in and digital design and prototyping, and then also shipping and packing. And it is crazy dry here at the moment coming into winter, so my lips are just destroyed. But yeah, a little bit chilly, so it's more of an engineering woody kind of morning. But alas, how does that look? That light's maybe a bit bright. No, that's okay. So welcome, Teardown Tuesday, where we look at cool things. We do teardowns, some reverse engineering, look at what makes our favorite products tick. And we also design some open source products and projects. We've already, do I have one? No, it's in the other room. We've already launched our first gizmo, the MIDI through gizmo, which is a really, really cool ultra slim 3.5mm MIDI through box designed to alleviate any TRS woes you might have. So it's got one type A MIDI in, one type A MIDI through for chaining multiple units, and then 8 outputs which can be selected as either type A, type B, we have tip active, ring active, or tip and ring active if you want to use a wire splitter. And that's for each output. So that's really cool. They went on sale for at a special launch price. I think now they're at regular price, which is still a bargain, $49 US. And you can get some cable adapters if you need those as well. They're not very much. So yeah, jump on board. We'd love to get some feedback. All the design files are open source, so they're up on GitHub. You can see the schematic, the PCB layout, the Gerbers, all that sort of stuff, and I'll keep updating those as I sort of streamline things and get it a bit more organized. So what we've been working on lately, if you're only just tuning in, is the Strymon Deco MIDI-fication. Ooh. Sorry, mouse. You're okay. Oops. Anyway, we have a Strymon Deco shell and a box of Strymon Deco parts. And that's sort of the complete internals of a Strymon Deco. And the idea is to MIDify it, to give full MIDI control over all of the parameters and see what other cool things we can do there. Now, Strymon, in fact, with very coincidental timing, not related to this, of course, yeah, definitely not large enough to pop up on their radar. Morning or evening, Alec. I got to be honest with you, mate, I don't understand that reference, but it's good to have you here anyway. Perhaps showing my youth a little. But yeah, so they've released that line, which is, is really cool, really nice to see that happening. But something I'm really passionate about is, I guess, MIDI control. I want to hope so. And also, in particular, keeping good gear out of dusty shelves or even worse, landfill, because we love gear and we want gear to be used and create music. And obviously appear on Instagram photos of pedal boards. But there's my little 3-year-old trying to break in. Yes, buddy. That is just in the middle of a stream. Would you like to come and say hello before you go for your haircut? No. All right. Well, come here. You can come and say hello. Come on. Come on. Come and say hi. All right. You're a little bit little. All right. In fact, that probably needs to come down. Oh no, it'll be fine. So yeah, he's in here. What was I saying? But I think there's immense value in creating a control board that can sort of MIDify things. All right. I love you, buddy. Go get a handsome haircut. I know, little man. See you, buddy. Oh dear. yeah, I think there's still immense value in this project, as I mentioned in the last stream, for several reasons. If you're DIY handy, then we're hoping to make this available for under $100 compared to probably $400 of a new device. I hope that we can do some cool stuff, which will sort of actually offer some new features compared to what will be available. It's going to be open source, so we can keep building and growing on it. I'd like to open source. I know there's some folks in the community with some some editor app type things, which could be functional with this project. So that's the state of things. Now, last week we were looking at microcontroller options because we're in the midst of a microcontroller shortage, crisis, semiconductor manufacturing, electronics manufacturing in general. Not in the best shape at the moment. Just try and reduce some of that glare. It's a bit better. Not in the best shape at the moment. But the Raspberry Pi 2040, which is the let me just bring up another window here. Guest. Which is the Raspberry Pi Foundation's first microcontroller. It's a dual-core 32-bit M0 Plus microcontroller, and pretty much has everything you would expect from a typical 32-bit microcontroller, with a couple of little quirks being that it requires external flash, but that's no big deal, and it does have some other cool, nifty features. But more importantly, you can buy it. You can actually buy it, which is the be-all and end-all at the moment. And it's got everything that we need. So in preparation for today, last week was mostly just looking at some design specifications, some different chips we might be able to use. I've just put together, or almost finished putting together, a bare bones schematic for it, and we'll go through that and look at some. This is going to be pretty electronics design focused today. So what I'm going to do is let's jump onto my screen here. Cool, you guys can see that. I'm actually going to, can I do that? All right, give me a second. I'm just going to create a new scene in OBS with my, let's call that. With like a browser window in there. So just bear with me through this, because that way I'll be able to do some Google searching, do some Googling, and there we go. Bring that down. No, I don't want to remove it. There we go. All right, so you guys will be able to see at least, the top bit of this screen. I'll try and keep everything of interest sort of up here. Can't see my cursor though. That's frustrating. Maybe instead of the window, we'll make it like a display capture. Better. Okay, so obviously some size issues, but kind of going to have to just deal with that a bit, I think. Yeah, that's probably going to have to be good enough. Anyway, so back to the main screen. So we have the Raspberry Pi. As you can see here, 2040. It is available, even you can just, a local electronics store, Core Electronics, has it in single quantities for $1.50 in Australian dollar bucks. Hang on, no, sorry, this isn't going to work because I need to have OBS on there when I'm not there, and it's going to get, sorry folks, there we go. This is unprofessional, but you can deal with it. There we go. All right. Get a black screen, but hey, new room set up on the fly. Good enough. What did we do that? Single units for $1.50. I reckon that's pretty good. And you can get it in large reels for like down to $1.20, but more importantly, we can get it. So that's important. Now, what I've been doing is just following along some of the recommendations from the Raspberry Pi Foundation's hardware design sheet, which basically gives you like minimum system schematics and things like that. So they've got this minimum board, which is just a linear voltage regulator crystal, the actual RP2040 chip, and some flash. And then, of course, some connectors and whatnot. So what we've got here is pretty much most of this. So we're going to go through and complete this schematic. Then we'll take a look at the GPIO pins, what we need to access, and really start building up the electrical schematic here. Why does that do that? Hang on a tick. All right. So. I'm pretty sure everything's looking fairly nice in terms of the actual chip. We've got our crystal here. So we're using a 4-pin crystal with some ground pads. Just got a placeholder resistor. They recommend 4 particular crystals depending on the nominal impedance. A damping resistor there. The value of this might change as we tune this RC network here. But yeah, some load capacitors here. Now, this particular crystal I'm using, what did I say I was going to use? Take a look at LCSC, because can't actually remember the crystal that I found. I mean, they're super common. Basically, when you're designing these clock circuits, if you're not aware, you've got this crystal, let me jump back here, you've got this crystal in and crystal out pin. And a quartz crystal, if it's manufactured correctly, has some particular properties where it will resonate at a very particular frequency. It's like a resonant circuit, but it has very, very high Q, the quality factor, which means it has this big peak at a particular frequency. And there's different, mechanically, if you take this quartz crystal and you tap on it or you disturb it mechanically, physically in some way, you will excite an output. And so you can actually do that with, you have an electrical output here, which excites this crystal, and you get a really nice clock pulse coming out of it. But of course, you need these loading capacitors, because the crystal is designed to operate with a load capacitance, and that's quite specific. You can't just whack any old value on there. So when you pick your crystal, it's going to have some load capacitance. The main factors are the frequency that it operates at, the fundamental frequency, the load capacitance required, and then also any sort of characteristic impedances of it, which you might need to be aware of. And this just helps dampen any unwanted, oscillation, stop you overdriving this crystal, things like that. You can get away with it in a lot of circuits. It's better to have it there, and you just use like a low value resistor if you don't need it. So we're going to take a look on LCSC and see what crystals they have available. So we want a fundamental frequency of 12 megahertz. It's specified in here that you want a 12, where is it? Anyway, yeah, you want a 12 megahertz crystal for the 2040. So I can apply that. There isn't really too much else that we care about, to be honest. I'm going to sort by availability, which I often do, because we obviously want things to be in stock. And these are all, you don't need to worry too much about the particular brand, as long as you get, something that's somewhat reputable. So LCSC typically has a lot of Chinese brands. They're, some of them can be a little dubious. Some of them, a lot of them are quite good. If you're designing using parts from LCSC, I would highly recommend looking at the data sheet, I find that's a really good indication of the quality of the part, I'd say, but also just the quality of the documentation is typically indicative of, oh, where's my coffee? Indicative of the quality and the attention to details and small things. So let's take a look. I believe we were looking at this 12 megahertz one with a load capacitance of 20 picofarads. We'll take a look at exactly what that means. So you more or less got two common form factors. You've got this flat, like metal can type form factor here, and it's got 4 pads on it. You can get active, like crystal resonators, which have a built-in resonator circuit, and they're an active device. You need to provide power. These are just your crystal, your 2 pins, and then they also have 2 pins for ground as well, which is really just shielding the package for EMI performance. And that's as opposed to something like this, this metal can type package. You can get in through hole or surface mount, and it is not a like a grounded enclosure. But these are either's very common, doesn't really matter. I believe the Pico board uses this type of crystal, and the minimum hardware design uses the metal can type crystal. Yeah, there you go. So let's take a look at this now. So it's got a reasonably good data sheet. It gives you everything we need to know. We can see here that the equivalent series resistance of this particular unit in the 12 megahertz to 16 megahertz range is going to be 80 ohm impedance. I believe the one they're using in the hardware design is a 50 ohm impedance. It's not really going to matter. You know, this resistor value isn't going to need to be a precisely tuned value. It's just there to stop it being overdriven. And this one we selected here has a 20 picofarad load capacitance. All right, and you can see the footprint there. So what that means is we have these 2 capacitors connected on either side of our crystal. And from the perspective of the crystal, these capacitors are connected in series. And you might know when you connect resistors in series, their resistances linearly add together. So if you have 2 1K resistors in series, they become a 2K resistor for all intents and purposes. And when you have them in parallel, then you get a lesser resistance according to a fairly basic formula, using the inverse of their resistances. With capacitance, it's the opposite way around. With capacitors, I should say, when you have them in parallel, they add together cumulatively. And when you have them in series, then you get a reduced capacitance. So with these in series, what we need is a 20 picofarad load capacitance external to this crystal. So whatever capacitors we have, if they're the same value, they're going to halve when we have 2 in series. So you would think, well, let's use 2, if they're going to halve, let's use 2 40 picofarad capacitors. Half that is 20. Perfect, right? But no, because we have to account for the parasitic and stray capacitance in our circuit. All right, and that's going to be really important. I'm also going to try and just get my OBS display window here. All right, that's a bit better. Sorry about that. Yeah, so we need to take that into account, and you can go to the ends of the earth measuring this if you like, but you'd be wasting your time to do so at these frequencies. When you get higher frequencies, yeah, you want to do, look at your characteristic impedances and parasitic capacitance of your PCB layout. But good rule of thumb is just add 5 picofarads. This is the universal engineer's rule of thumb, 5 picofarads of capacitance to account for the traces and whatever might be going on with adjacent ground planes and things like that. So what we need to do instead, and you add that for each capacitor, or sort of like the overall result. So if we have 2 30 picofarad capacitors, then half of that is 15, and our 5 picofarads of parasitic capacitance is going to bring us up to 20. Now, it won't be exactly 20. Of course, you've got the tolerance of the capacitors, our rule of thumb, 5 picofarad capacitance, all of that is just approximations, but it's going to be close enough for the intents and purposes of this circuit. So make those 30 P capacitors, or they are a bit squishy. Let's bring that down a bit. Very good. And this is what I got up to just preparing for the stream. Now, let's go back to our kind of documentation reference. So supported flash chips, I just grabbed the one that they recommend. It's the W25Q128JV SIQ. And it's just a quad SPI flash. Nothing particularly exciting about it. You can use lower values and things like that. In fact, jump back here. I'll run you through what's going on at first. And they use the same trick in the hardware design documentation, but with this, these flash chips, they require the chip select to be high during power up, and if they're low during power up, then what on earth have I done here? Why is there an extra resistor here? That's not supposed to be there. Let me just see. I was kind of just went a bit ham and copy and pasted some of these recommendations. Why has that happened? All right, we might make that a bit bigger. Anyway, sorry about that. So I was just looking, and you've got these two 1K resistors, and really this one should be a weak pull-up, and this should be a much stronger pull-down resistor when this switch is active. To explain what's going on here, let's just make that 10K for now. We've got this pull-up resistor, so that because the chip select pins on the SPI hardware is an active low signal, so it pulls it high, and this chip will start up just fine. When it is low on the chip select line, then the Raspberry Pi, because this is connected to the chip select line on the 2040, detects that and goes into a special bootloader mode, which allows you to just drag and drop firmware images via USB. It enumerates as a mass storage device. So that's what this switch does. So if you hold this switch down when you power it up and connect it to a computer, it will enumerate in that special bootloader mode. Apart from that, nothing too fancy. Our decoupling capacitors. Then we've got our SWD. That is really annoying. Our SWD connector here. We're using a 6-pin JTAG. Tag Connect footprint. It's lately become my favorite footprint for SWD connections. I use different ones like actual pin headers or edge connectors, but this has become my favorite one for sure for all but the most compact layouts. I think so. We've got our crystal, then we've got a run switch here, and this is just like a reset circuit. I need to check that I've got this right, because whether this is an active high or an active low, and basically by toggling the wrong here, more or less this will it's like a reset pin for the microcontroller core. So trying to take a look. Is the reset active low? Yep, great, cool. Most of these are active low. I just wanted to triple check. So we've got a little reset push button here. Then we've got some decoupling capacitors. These are for the like our VREG in and VREG outs for the internal voltage regulator. So it takes 3.3 volt supply input, which I haven't put on those nets yet. And then you can either externally supply 1.1 volt like core voltage, or you can just let the internal regulator take care of it. Now, I would like to double check. Let's go back to this reference page. The power connections, because I can't remember what you actually have to connect here. So okay, so for pin 44, where are we? We are Where is pin 44? Ah, there. Yeah, so that does have to be connected to 3.3 volts. So the only pins that are left not connected because they've got this 1.1 volt there is 45, 23, and 50, which is 45, 23, and that'll be pin 50 in there as well for our two digital VDD pins. So let's go ahead, make some connections here to, helps if we go back to the schematic. So that needs to be connected to 3.3 volts, as does this power supply here. Let's put it there above our ground pin, sure. Yes, we're going to change that net name. All right, so this is shaping up well. And they remain sort of unconnected. They've got an internal connection. Great. Now, looking at this power connection here, going back to our side screen, we've got our termination resistors for a USB line here. That's looking good. We've got our decoupling capacitors. We need to add in our power stage. That'll be important. But I think everything else is pretty done. Our flash is looking good. Do they give a recommended value for R2? 10K. Yeah, so exactly what I put there. You just have a 10x fact there. And then our crystal, they've done the exact same thing, but this crystal would have a slightly different required load capacitance. Looking at that, probably 7 to 16 picofarads or 18 picofarads required. All right. Now, USB, we've got our terminating resistors all done. Now it's time to look at some I/O. Lovely. I'm going to go and save this. This is our control board. And if we go ahead and look at the PCB layout here, switch over to our PCB view, we've got all of these packages and footprints here. Now, we'll jump back just a hot minute. Let me go to our, where's our Gizmos folder? Okay, there we go. Our Gizmos folder here, we're going to open up the whole project file and just take a look at sort of where we are in a 3D space perspective so we can see how things might start to fit together. So this is our rough 3D model of the enclosure, some foot switches, our control board here. So this is shaping up fairly nicely. Lots of room for our microcontroller to go on here. Now, if you're tuned in last stream, you saw that we were having had an issue with the 3D model of some the USB connector and the 3.5mm jack connector. With their 3D models, I've fixed that up. So before we go any further with the main control board design, I'm going to open that up and close some of these tabs maybe. I can't see my tabs, but there's a lot of them. I am a notorious tab fiend. I think I don't like closing a tab in case I need it again later, and so by just now habit, I will always open a new tab rather than search over an existing one. So that's good. Let's update these parts. Okay, so it doesn't like this. What I'm going to do is just delete. I tried adding another dummy part. Anyway. All right. I'm going to delete these. I'm going to add new ones in just from scratch. All right. So connectors. Close that, get a bit more space going on here. We want USB-C type. USB type C 2.0 connector. We also want some of our, where are we? These ones, our 3.5mm. Yes, Fusion. Let me place it. Honestly, there we go. So now we should have these parts here. We're going to push this to a 3D board and see if things are kind of playing nicely. So on our 1mm grid, which should be visible, there we go. going to ignore those violators so it doesn't try and auto place. You know, I know that there's going to be enough room once I put some proper design rules in. We'll just put those there, I guess, and there. We can probably put our connector to the main board behind the USB-C connector somewhere. Let's just move it down so we've got a bit of space. I don't know if we'll do like a MIDI through as well as MIDI in, maybe. Who knows? All right, let's just save that. Put this to a 3D PCB so we can take a look at what this is going to look like. And if you missed last week, the idea is that it's going to be really tricky to mount the USB and the MIDI connectors, like the TRS connectors, on the main board because of some of the tolerances of the enclosure. And trying to make this a DIY-friendly product that you know, anyone just with a basic hand drill, and I'd say in the kit we'd provide a template so you can get it pretty close. You can just sort of put over the side and just drill a couple of quick holes. So having this daughter board that you know, decouples it from the main board is going to really help with that goal. So yeah, that's looking much nicer. Much nicer. So that's just a bit of a catch up on where we are with the 3D design, because I need to work out roughly where this board's going to go before we can start laying some components out and finishing up the electrical design. So let's go back to our side panel, insert our 3D PCB into the project here. Cool. Just leave it there as is. And I'm also going to open up the enclosure so we can make some changes, some modifications. So yeah, we might have to do. I didn't want to put the enclosure in like this because I'm pretty sure then when I, like, you know, show or hide faces, it's going to show or hide it in there. What I want to do is insert a derive, I believe. But just give me a moment. This is going to make, we only have 2 viewers, so that's fine. Hopefully you guys won't mind. I just need to duck away for 2 minutes and grab something for this. 1 minute. Sorry about that, folks. Didn't exactly make for great viewing there. Just my little rabbits. I've got two sweet little bunny rabbits, and they got out, and I could hear them running amok, and I just had to go and put them away before they caused too much confusion and delay. All right. So we're looking at our enclosure design. Now, what I might do is go back to our project and remove the enclosure. Yes, I know you're not going to like that. I'm going to insert it as a derive, which means we can make changes based on like what parts of the component are visible and things like that. So add that as a derive into here. Whole thing. Cool, there we go. Now, go ahead and insert this. Hang on, what am I doing here? Insert. Let's insert a different one just so I like to make sure it's the top left one. So that is a join there. I think like 14.9 millimeters up is going to be about what we want, but we need to rotate it, of course. So let's rotate that minus 90. Perfect. Now, a little nicer, or more nicely, I should say, look at that. Sweet. Perfect. A little bit extra there for some tolerance. I'll probably we'll just make it 15 because that's going to butt right up against it. Cool. Now our foot switches are going to go there, rotated 180 degrees. Let's bring them down down about 6 millimeters. Seems quite plausible. And here, same point, 180 and down by 6 millimeters. All right, there we go. Back again. It's looking good. Now, this board, where's it going to go? Because I feel like, I mean, let's rotate it. Okay. Rotate a component, our USB board there. We need to select an axis to rotate in, don't we? It's our origin axis, we'll rotate it. Honestly, it takes me so long to work out what's the right axis to rotate it in. That away, so minus 90. Also want to rotate it in that axis. Yeah, I think it'll probably go on this side, if for no other reason than, I don't know. What do you think? Right side or left side? Does anyone have a particular preference? I don't really know if it matters that much, to be honest. I'd like it to be close to the power. So if power connector is going to go there, could get a little bit cluttered, I guess. We might put it over on the other side so it's next to the power source for our USB, so we can keep our grounding a little bit tighter. So what we might do instead, wait, let's undo that move. Let's TRS board, go ahead and rotate it about that axis, 90 degrees. Cool. And you can go about, hate trying to move these in 3 dimensions sometimes to just get rough spacing, but I'd say somewhere about there. It's going to have to be a fair bit more compact, isn't it? There is room sort of to go more underneath it, but so what we're going to have to do, I'd say, is put it like next to that pot there so we don't interfere with the LED. Okay, that could work. Might need to flip it, maybe, so those connectors aren't too high. Let's try that. We'll rotate that about, which axis do we want to? Maybe that one. Yep. Oh, it's going to rotate all the way that way. Thanks. All right, back to here. At the top there, and we're going to move it down. Yeah, I think that could work. If you guys have any comments on this process, by the way, feel free to let me know. You know, this is I want this to be a fairly collaborative process. So, any design suggestions or recommendations? Shoot. I think that'll work pretty well. We've got a nice amount of clearance. The holes won't be too far from the top. Yeah, it could be good. The other thing we could do is sort of cut away part of that board and drop it a little bit lower, maybe. We'll see. But roughly there's going to be where we want it, I'd say. Nice. Okay. All right. Well, I know now that I want to keep that, and why I did this, I want to keep that part of the board fairly empty. Cool. So I'm going to save that, and we'll return back to our main board design. Okay. So where are we? Alrighty. We're here. Wait for it to load. There we go. Get that out of the way. So we've got our quad spy. We've got our SWD connector, which is the programming header that we'll use. I'll just leave it there, I guess. Now we need to look at what external bits and pieces we need. So coming back here, we've got our pots, and we've got our LEDs. No idea what that switch is doing there. What S1? What's S1? Show S1. Oh, that's our toggle switch. Of course, we need that. Okay, well, we're going to need some foot switches, aren't we? Now, we just need some foot switches. Looking at this board, let me switch to the overhead camera for a second. So this is our the original control board, and the foot switches have these larger connectors, and these are, I think that they use them on all Strymon pedals with this fairly chunky connector there. We actually use that's the exact same brand of foot switch, but with a smaller connector, a JST 2.0 millimeter pitch connector. These ones are pretty chunky. I remember Simon did a bit of a dive to try and find out exactly what type of connectors these are. Let's move that camera down a bit. I'm not framed overly well. Still not framed overly well. It's a little better. And I can't remember the exact name of these series of connectors. I've got it written down somewhere. We found them, but they're the exact same family or type of connector as those found on computer, like PC fan headers, if that helps, but a 2-pin one, obviously. So I believe you cannot get them in surface mount, unfortunately. So the way that we will, I'd imagine we'll package up this project is by offering 2 versions. Now in either one, you'll get the PCB with all the surface mount components already soldered, and then we'll offer it just with the through-hole parts, because most people, if they're DIY, they can solder some through-hole parts like the pots and whatnot. We'll offer it with all of those loose, so it'll come with everything, but then you just need to solder those through-hole parts yourself, or for a little bit extra to cover the time and labor, you can have just everything ready to go, pre-soldered. But it'd be nice to have these as SMD connectors, but we can't get them. Now, I don't know. I'm going to have another look to try and find what type of connector they are. I'm not sure if Simon is currently watching, but scroll up, see if I can find this type of connector. Where is it? Because then we can just go and find a footprint for it quickly. Connectors. Okay, they are a Molex KK254 connector. So we're going to take a look at Snap EDA. Typically, I create most of my like PCB footprints and things like that from scratch or from existing footprints that I have. For things like this, though, you know, where it's not like it's a basic through-hole connector, I don't need to worry too much about getting the pitch of the pins perfect for some, you know, obscure SMD part with underpackaged pads or something like that. Snap EDA is a really good resource, I find, for getting some, you know, some footprints and parts fairly quickly. So this is what we want. The question is, do they have one with a 3D model that is exactly the part we're after? That might be a bit of a long shot here. Got a bit of a doubt. Oh, Simon's good. He sent me the connector part. He sent me a part number. Ooh, thank you, Simon. Let's. Oh, no, it just didn't copy. That's great. There we go. Ah, okay. It's the wrong photo, but the part number's right. Straight header. Simon, are you sure that's the right part number? Because that's saying it's a straight header. We want a right angle header. Let me take a look at this. So we're going to look up this URL, part number, Molex. Molex don't have right angle connectors. Okay, so this is not, in fact, a Molex brand connector, it would seem. I could be wrong, but, you know. Okay. I'm going to have to manually try and find this. Honestly, or I could just stop being lazy and look it up myself. But I just want something like that that's flipped around. I just want to try and make sure we can match the exact type of connector that they're using here. If we're supplying it for people, I think that would be good. So that's right angle, but if you look at, let me show you the board again. It's got this, so it goes right angle, and then it's got the like the locking pin on the like kind of close to the board, which means that these other ones here are going to be the opposite way around. So we want something where that locking connector is sort of on the same side as the right angle pins, which none of these look like they are. Which is a bit frustrating. You know what? We're going to leave the exact footprint. We're just going to add in some generic like pad switches. So let's go to switches, and let's just get a momentary switch, I think. Okay. Do we have just pads in this library? Yeah. We'll use these for now. So these are going to be our foot switches, and we'll create our foot switch circuitry. So what we're going to want is some debouncing for these switches. Now we could use, you know, an external Schmidt trigger perhaps as well, but just like, you know, a low pass filter is going to do the job just fine to get rid of some, you know, some spurious edges on here. So let's go ahead, and I'm just going to steal these resistors. If I have any on here. No, that's all right. Well, we want, doesn't really matter exactly what value there are. We can, you know, tune the low pass filter to, you know, we can look up on a scope the bounce characteristics of these switches and tune a filter to be exactly, you know, what we want for those. We're using some 1K resistors somewhere else, so we'll just start off with some 1K resistors. So low pass filter here, and we'll borrow some capacitors. We'll start with some 100 nanos. I guess that's probably good. This here. And we'll okay, connections. Now we're going to want these to be active low switches. So this is going to be high. Now I believe the Raspberry, the 2040, we should check if the Raspberry Pi 2040 has built-in pull-up resistors, because if not, we're going to have to add those. Okay, RP 2040 data sheet. Let's take a look. It's probably going to be a large document we're going to have to search through yet. 634 pages, as you would expect for any microcontroller data sheet, especially a 32-bit one. Pull up. Pull-ups. Okay, so that's interesting to note. USB pull-ups are provided internally. The pull-up enabled. I just want to know if there's GPIO pin. Okay, enable pull-up resistors. Oh, that's for the USB. That's the USB control register. I want to know if external interrupt pins. External interrupt. External interrupt signals connected to the controller. I want to know if there's GPIO. You would assume so. Pretty much every microcontroller you can configure rising or falling edge. External interrupt pending flags. Okay, GPIO, external interrupt requests, level or edge sensitive. That's good. Does it say anything about pull-up resistors? I just want to know if we need to put them external or not. Cool. Anything about, this is the function select. You can choose between, all your UART modes and things like that. This is not the easiest thing to find. Interrupts, great. Yeah, now we've got interrupts, pads. Okay, a pull-up or pull-down resistor can be enabled. Okay, great. So it does have internal. It sounds like, obvious. Of course, it'll have internal interrupts, but you'd be surprised because I've been caught out before where you assume it does and it doesn't. And we all know what happens when you assume. So I'm just going to have a fairly basic low-pass filter connected here, and that's going to go to, we've got space to add a nice label here, I think. That's going to be called, call that FS1, foot switch 1. Foot switch 1 will say that that's the one on the left, and then we'll just copy that to here. But this is obviously not going to be FS1 as well. That'll be FS2. We'll just tack on our ground. Cool. All right. That's looking pretty good. Pretty good. We know that there's going to be a pull-up, sort of pulling that high, and then our switch is just going to be a foot switch. I wonder if it might look a bit neater. Ugh. Putting it that way. Yeah. For the sake of neatness, we're just going to move this around a little bit. There we go. That looks a bit better. I know it sounds silly to kind of, spend, or looks a bit silly spending time mucking around with the orientation of your components like this, but believe me, a readable schematic saves you a lot of time and pain in the long run. It's well worth just making sure that things are nice and tidy and organized, when you're doing it. So there are 2 foot switches. We'll kind of group these, these parts together as we're assembling or, cleaning up our schematic, our foot switches. What else do we need? We've got our LEDs. We've got this switch here. it's going to need some circuitry as well. So we're going to take the same, oh, sorry, I forgot I was not on the main window. Going to take the same approach. We've got our foot switches here. Same approach with those. Like for our toggle switch. But this is the wrong type of switch schematic. We need an on-off-on type switch, not just a double throw. No. Although, hang on. No, of course, it's the exact same type of switch. There's just this middle position here. My brain is just absolutely wigging out. Okay, so this switch is going to give us 3 positions. Okay, when the switch is in the middle, neither of these pins are going to be connected to the middle pin. So these will be our 2 outer pins. Then it can be either this pin connected or this pin connected. So if we provide a ground, we ground that there. Right, and then we're going to just kind of copy our low pass filter, debouncing circuitry here. Spread this out a little bit more. Then we'll copy that again. Make this nice and readable. There. Is that the best layout for this? All right, well, let's just get things roughly in place, and then we can tidy them up. This is going to be not foot switch 1. We'll call it toggle A, and toggle B. Yeah, I can definitely make that a bit neater. That's not great, is it? But it'll, I think it'll, what I just said about making sure your schematic's nice and clean every time. Bit of a do as I say, not as I do going on here, but that's fine. Doesn't look too bad. It'll do for now. So we've got our toggle switch there and our foot switches. Cool, this is all coming together. I'll just bring that ground down to that same level there. Lovely. Now, what other hardware elements do we have that we need to add to our schematic? Because we've got our kind of our microcontroller core looking pretty good. We need power, of course. So I'm going to keep all of our like microcontroller IC elements on one page, then our hardware inputs and controls on another page. Then we're going to create a new sheet here. This is going to be power. I might go ahead and add some frames to these now. Just start really tidying things up and making it look a little bit nicer. I think I've got one in this Fusion library here. That'll fit everything. Just an A4 page. I'm going to take all of this and put it in a frame and just start organizing and keeping things nice and tidy. We're going to have to change our layout a little bit. Go ahead and add some sections and some labels for all of this, of course. Let's select our foot switch bits and pieces. That can go there, I guess. And our LEDs, of course, can go there. We can go ahead and clean that up in a little bit. But, a little bit cleaner. We'll move all of this back to the origin of our schematic. It's going to be nice and easy to read. It's actually good doing some open source projects like this because it forces me to actually put some best practice in and make things look nice and readable, given that other people are going to be looking at and using schematic, not just myself for internal use. So we'll put that there. We'll go ahead and add some some more labels and things like that a bit later. Put these down the bottom. Our flash programming connector. Oh, that doesn't fit overly nicely, does it? I want things to be too squashed. But there for now. That. Yeah, cool. Not too shabby. Just save this habitually. All right, let's go ahead and add a frame in from the start. A bit more sensible. So we need some power. We need to work out exactly how this is going to be powered. Now, I would assume that this board, I've kind of overthought a little bit here, this board provides 3.3 volts on the control board, but we're definitely going to want to check that because this could be running at, the DSP could have like 1.8 volts or 2.7 volt GPIO pins or things like that. So it's definitely going to be worth us double checking that. I'm going to go and find a power supply, plug this in and get the multimeter and take a look at some of those voltages. Just a second. All right. One by multimeter, one by volt power supply. Like I said, I only moved my desk in here yesterday, so I'm still kind of getting things up and running a little bit. Alrighty. Let's switch to my overhead camera here. Sorry, I know the quality's not great. I'm working on trying to make that a little bit better, but yeah, it was a little bit lower priority for this morning. What I really need is a keyboard tray, slide out keyboard and mouse tray. That would be pretty nice. All right, bring this a bit closer. There we go. So got a multimeter here. Oh, sorry about that. That wouldn't have been pleasant. Put that on voltage mode. We'll go ahead and plug this cable back in. Which side of the connector's on? They look like they're on that side. Why is it? Oh, okay. Yeah, I'm thinking of this the wrong way. It folds over that section there. Make sure we get this seated properly. There we go. Don't want it making intermittent contact. There we go. All right, and now let's plug in. That's a top. Contacts on the top. Okay. Power. I can't remember if these have a switching circuit on the input for battery. No, we're ready to go. Good to go. Now, is this the bypass foot switch? No. Is this the bypass foot switch? Can't hear that relay clicking on. Does it have a like a full bypass? I'm not exactly sure. Anyway, here's our board. Now, let's take a look at some voltages going on here. Where are our ground points? The whole back is ground, really, isn't it? So we can take one of these as our ground, and that's going to go. Quick continuity test to double check. Great. All right, that's our ground. Now, we'll go ahead and look at some voltages here. 0 volts. 5 volts. This is a 5 volt board, 3.8. These might be the pots because we're getting these various voltages. What we'll do is we'll put them all to max. And I mean, we can actually probe the voltages across the pins here. That's going to be the... Okay, so that's our supply voltage, 5.2 volts. Very interesting. And let's put that in half and just double check the pin out. Cool. So that's our... Okay, so that's our signal. Holding those with one hand. When I turn this, it sweeps that voltage. So this is a 5 volt board. That's, although this chip would have been released in like the late 2000s. You know, it's a pretty old chip, to be honest. Maybe a little bit after, like this. Maybe it's an updated model. I'm not exactly sure, but you know, 3.3 volts wasn't quite as common back then, so it stands to reason that yeah, this could be a 5 volt logic going on here. All right, so we know that it is a 5 volt board. Did not expect that, to be honest. I was expecting 3.3 volts or less. But our Raspberry Pi is going to be running at 3.3 volts, so we're going to need to interface, to that. So we now know that we need, we're going to have a 5 volt input supply. Okay. What we'll do is we're going to go ahead. We need a 3.3 volt regulator. So what am I going to use? Don't need too much current, so we're going to use this sort of Jelly Bean generic nice and compact 3.3 volt regulator here. And it's, you can see it's I think a SOT 23 package. Where are we? Here. That's an 0603 resistor, so nice and small. It'll only do like 100, 150 milliamps, but that's certainly all we need. We don't need to be driving much with this at all. So I can't, you know, we'll have to look up, because this is just a generic footprint, we'd have to look up the exact chip that we're going to use in terms of what it requires for decoupling and stability capacitors, but we'll just go ahead and add some generic, you know, some rule of thumb parts, and then we can put in some exact values later. So we're going to want at least, you know, some decoupling capacitors on the input and sure on the output. As best practice, let's go ahead and get some supply symbols in here. 5 volts coming in. We're going to want 3.3 volts. At some point there, we're going to want some grounding. All right. Now this enable pin is going to want to go high to enable the regulator. We don't really need to have any control over that. Where are we? Connect our ground. Cool, that's all looking good. Oh, why did I do that? This over here. Although I really do want some more space there. I don't like it being connected straight to that junction. Ah, here he comes. He's back. Look at you with your cool haircut, buddy. Daddy's still working, unfortunately. He's doing a video. But you are the most handsome little man ever. We've had the before and after haircut look. Let's see. Is this not the most handsome little chum with his new haircut? You got a haircut? Yeah.
I'm Simon.
Yeah, you were talking to Simon, weren't you? Simon's gone. Mwah.
Oh, Simon.
All right. I'll be mate. Go
Smoothie.
have a smoothie with mummy for me, buddy.
No shower.
No shower. Can you close the door on your way out, please? You go. Close the door. Good boy. Thanks, buddy. Watch your fingers. Nice. Oh dear. Okay. How are we doing for time? Yeah, we're all right. We've got lots of time this morning. That's not really the most elegant looking. That looks disgusting, doesn't it? Yeah, let's just condense this a little bit because that looks gross. All right, so we've got some decoupling capacitors here. In a little bit. Then we're going to want some bulk capacitors as well. So I'd say maybe some allowance for, well, we want some 10 microfarad caps. Yeah, I'd say we probably will. So let's add, yeah, that's the part I want. Let me add it. Allowance for some 10 microfarad. You know, we don't have to populate all of these parts as well. And then it might only want like a 1 microfarad or a 4.7 microfarad. So in our ceramic 0603 footprint, let's just go ahead and add some. I swear I've got some here in this library. Yeah, some 1 microfarads. And you'll notice that I'm putting them in order of kind of smallest to largest, closest to the chip. And that's intentional because in order for these to be effective, especially if you're talking about decoupling, then you want, yeah, this layout is not great. I want to extend these a bit because I'm getting a bit claustrophobic with these nets. That's better. You know, in order for your decoupling to be effective, you need to reduce the inductance of your traces, and you know, long and short of it is that you want your decoupling capacitors to be as close to the chip that they're decoupling as possible. So naturally, we want to put the smallest capacitances closest to the chip, and then the further away we get, they're more for like bulk capacitance and filtering. They can be a bit further away, and that's fine. So I'll add these here and add some. Probably only want to go 1 ground symbol there. There we go. Yeah, that split signal there is just doing my head in. Looks a bit nasty, doesn't it? A terrible idea from the start. All right. Yes, we'll merge that now. So it's sort of just mirrored this capacitor selection on both sides here. I think that's gonna be fine. So we've got, you know, we can fit a 4.7 microfarad capacitor in this same 0603 package if we want. Then we've got like a standard 5mm diameter electrolytic there for some decoupling if we need. So just make that 10 microfarad. Just fine. Now this is going to be our 5-volt input. And we're going to have our 3.3 volt output. Now we're going to add some filtering to the input of this board, but we'll do that when we add, you know, the connector, and then we'll just put our 5-volt symbol after that as our symbolizing our filtered 5 volts. So that's our linear regulator there, our low dropout regulator. Now we need our connector, which I don't actually have a footprint for yet. So that might have to be a next week kind of thing, but we know that it's going to, you know, just going to have the output of our signals and everything like that. So we'll leave that. Now we've got our power. All right. So this is looking pretty good. We've got our microcontroller, the RP2040, our flash, our programming connector, our various, you know, controls and things like that, and the circuitry for those, and some basic power here. We're also going to need our I/O, because the potentiometers, as opposed to just, you know, with the original board, the potentiometers send their analog voltage right back to the main board. But in this, these potentiometers are connecting to our microcontroller, which means that we then need to take those signals from the microcontroller and output them back to the board because there's no digital communication interface that we can use here. So we're talking a bit last week. We'll add a new sheet here for this, that we're going to need an analog to digital converter, and they can be a little bit hard to get at the moment. But there's that sheet on. A good candidate here will be the MCP 3008 or 3008. Let's go back here. So MCP, you can get in surface mount. I just forgot that this part comes in surface mount as well. It's quite an old ADC. It's fairly low performance in terms of, you know, modern high performance ADCs, but it's more than going to do the job for what we need, and it can operate on a single supply voltage up to 5 volts. It's going to be very important. I mean, we're going to use 3.3 volts for everything but the output signals anyway, so no big deal. But okay, and while I'm designing this, I'm thinking that, you know, I want to make this board a little bit generic, or at least the schematic, so it can be repurposed for other things, because I could see this project expanding out to not just the other Strymon small box pedals, but using the RP2040 as the basis for lots of open source projects. You know, maybe we could, I remember Alec was talking about it'd be cool to do like a Noble ODR in a MIDI control kind of format, so a replacement board that you could put into your original enclosure, perhaps. That'd be cool. And so maintaining, keeping some repurpose, you know, repurposing of the design in mind is going to be important. So having, you know, these options for whether it outputs 5 volts or 3.3 volt logic is going to be fairly important. So it's, you know, it's got everything we need. It's got 8 channels of ADCs, which is plenty. So that'll allow us to use this one chip for designs up to 8, you know, pods to read, because the RP2040 only has 4 onboard ADC channels. So I believe I've already got this in here. Preparation for the stream. MCP. Here we go. Here we go. So let's add this in here. Now let's see what the data sheet requires for. Sorry about some of the noise. I'm having a grandparent day for the little man. So, all right. Does it have any kind of, you know, typical application schematics to just look at if it has any weird decoupling requirements or things like that? Here we go. So buffering the analog, it's not a low impedance source, blah, blah, blah. We don't need to worry about that because we are in control of that. Layout considerations, it just wants a standard 0.1 microfarad. Yeah, we're going to want to keep our grounds separate, of course. A bypass capacitor of 1 microfarad. Great. Okay. What's that? Then like 0.1 microfarad as well. It's not going to hurt. There's nothing particularly stringent about these requirements. Like I said, it's not an overly high performance component. So we'll go ahead. I really don't like how, you know, really don't like that layout. That's not great. We are going to separate our analog and digital sections, I think. Yeah, so we'll use sort of some separate grounding for that, and have some. Yeah, but sure. I don't really like this footprint, so let's go ahead and change. This was again from Snap EDA for the symbol. So let's open this part up. All right. And where's the symbol for it here? Okay. So I'm going to use decoupling from that pin. So I'm going to move that here, and it's also VDD, so it's going to be our digital power. So I'm going to make that, just give those a bit of space, and then we can have our D out. That's better. It's not quite as condensed. Probably some decoupling for our VREF pin, I'd say as well. All right. just bring this in because there's no need for it to be such a large symbol, in my opinion. Save that. Okay. Yes, that's my multimeter. Go and update. Of course you can't. Why? See, it's like while it's saving in the background, it's got to save it to the cloud, and then it puts it in this temporary library. I just don't understand why Fusion does things like this. If you're part of the Fusion dev team and you're watching this, this is what it actually looks like to run into some of the frustrations of using your product. It's so good in so many ways, and then you go and just do things that someone using your product is going to run into issues. And it's like some of the people in charge of some of these things have just never actually done this isn't even a complex project, but it's like you just haven't test driven it, because it's enough to make anyone doing a layout really cranky. All right, so put some 100 nanos. We're going to want a couple of those. Want some 1 micros, where I think I just scrolled way past them. Maybe not. Here we go. A couple of those. I'm just going to go back here and see what it says about the analog and the ground. If it has any particular requirements for that, we're going to want to keep those separated, obviously. Clock speed, buffering, layout considerations. Separate as much as possible with no traces running underneath the device or bypass capacitor. That's basic layout 101. Use an analog ground plane to keep ground to the devices, trying MIDI connection start configuration, reduce noise. Yeah, of course. So, separate internals of the device. Internally connected through the substrate, which has a resistance of several ohms. Both connected to VSS on the board. Okay. Both an analog and digital ground plane are available. Both the digital and the analog ground pin should be connected to the analog ground plane. That's interesting. Okay. Kind of wild. I didn't expect that, but we'll put that ground plane right near the we'll use some nice tight grounding. Like I said, not high performance, but good to follow best practices. Anyway, let me check the pin out in the data sheet that it sort of matches what's going on here. We've got VREF, yeah. Okay. What requirements does it have for VREF? And why is it not mentioned here? It's like it missed our reference input. The reference input not just follow the supply voltage? No? Okay, that's interesting though. Calculation. Don't really need to worry about that. Yada, yada, yada. All right. Nothing too much to worry about. So can have our chip select pin because it's a SPI device, and our clock. I really want to move those. I don't like that they're so separate. Let's go back to our symbol and make some more changes. I'm gonna bring those down here. Bring our analog pins up and just try and separate the analog and the digital circuitry a bit. In fact, we'll bring those pins down again. VREF there. We're actually going to undo some of what we did just before, make this a little bit bigger so that we can give our analog pins just a little bit of visual space to help with our layout. Cool. Okay. Although, we've got like our ground, our analog ground down the bottom. So what I might do is swap these so that sort of we've got top is our digital and lower down is our analog. I think that's just going to be a little nicer. A little bit nicer. There we go. Yeah. Bring all this down. One. Cool. I am a bit happier with that. Now, is this going to update, or do I need to wait for an hour for it to push to the cloud? Yep, thought so. Oh, boy. Just add it back in because it's going to take a while to. Anyway. Okay. So add some pins for all of our digital signals here, and we'll name those accordingly. So this is going to be SPI, not quad SPI, so just SPI clock. I just want to one of these kind of labels, SPI. This is going to be data in is going to be master out, slave in. So we'll use MOSI as the more typical SPI designator, and we'll make this the ADC chip select pin. On here we're going to have SPI MISO, master in, slave out. Nice. Okay. Let's add some decoupling. Probably don't need quite this much decoupling in hindsight because there is only one supply pin, so get rid of these two. Also add some localized stability. We've already got localized stability on and some decoupling on the pots to help keep that supply voltage nice and clean. Connect all these up, and it wants this to go to. Do I have a ground on here? No. All right. There we go. Now, let's kind of just bring this out a little bit so we can add a maybe 3.3 volt for here. It's a little bit ugly, not the neatest job in the world, but good enough for Australia, as Dave Jones likes to say on all of his videos. So good. That was dumb. Just made it more cluttered. Cool. All right, that's looking pretty good, I think. Just gonna sort of, for the sake of sanity, move that across to here. Whoop. Hang on. See you, buddy. You have fun with Granddad, all right? Got everything you need, buddy. Yeah, I'm live. Extra over. See you, buddy. Yeah, that'll be fun. That'll be fun. See you, Dad. Yeah. Got a smoothie out of that. Oh, by the way, Nick said he left his backpack here. Sure. That's big enough where it is. And a smoothie. All right. Okie dokie. So, then we'll sort of put that there. All right. Now we've got these analog sections. Our VREF is going to be connected to 3.3 volts. All right. Bit of a headache this morning. I think I slept on my neck. Funny. Anyway, and we're just going to give these generic channel names. And then if we're doing an application where they require any particular buffering, then we'll sort of sort that later. There we go, and we'll name these ADC in 0. Cool, thanks for that. So on and so forth. Oh, go. There we go. Okay, that's looking quite good. So we've got our analog to digital converter there. Now we've got our pot here. We're not really going to need to add any sort of buffering or anything like that. It's not really worth doing, I don't think. What kind of impedances, when it says low impedance, what exactly does it require for low impedance? Yeah, so we want to, to remove aliasing noise, we're going to want a low pass filter, which we already have. It's going to be fun, honestly. I'll use some low, like low impedance, maybe even 1K pots. It's not going to be a problem. So what we might do is take those labels off, actually change those, change that name to ADC in 0. Ugh. Big other parts of the schematic, so I'm going to spread this out a bit. So I'm just clenching my jaw a little bit while I sleep, which is not ideal. Need to ran out of room a bit there, didn't I? That's all right. Sort of, not really. Just for the sake of neatness, let me move this around. And I also moved our LEDs. I had everything just the way I wanted it. Funnily enough, even if I'm not streaming a design, I tend to just talk to myself like this anyway. So it's not incoherent mumblings, not anything out of the ordinary. Vertical space to lay it out like this. It'd be really nice if I did. Really nice if I did. And it's going to be just so I'm going to have to get this up a little bit. It's not the prettiest solution. Not at the end of the world. All right, cool. And we'll just sort of put things back in roughly where we found them. Something like that. Change this up. Honestly, this is so much of, if you're going to do like electronics design and things like that, just moving things around on a schematic, it'll spend a huge amount of time. Okay, save that. It's looking a bit better. Probably go for a slightly longer stream today. I want to try and smash a bit of this out because because I've got to go and get cracking on some more gizmo and bridge assembly and do some editor app testing today. Okay. All right, so now we can get the signals into our ADC, which is nice, but we need a way to get the data from our ADC out. So we're obviously going to want to use a SPI interface on our RP2040. I was just not even on the screen the whole time I was doing that. I'm so sorry. It's been one of those mornings. Anyway, we've got our ADC here. Got our pots here. Sorry about that, folks. Okay. Now, we need a DAC or a DAC in order to get those signals out from our board. Now, we do have a couple of options. Could use a dedicated DAC. Not exactly ideal though, because well, I mean, so it is, but it's going to be, extra cost, extra board placement, extra signal routing, all that sort of stuff. But RP2040 has quite a large number of built-in PWM channels, which they actually use for, you can filter and then use for analog output. So what sort of frequency are they running at? Okay. What frequency can they run at? I just want to know the max frequency. Didn't tell me. Cycle double buffering. That's all nice. Clock divider. Okay, here we go. Sweet. Lower frequencies. We can run these in the megahertz, so we can really, get them nice and high above the cutoff for our low pass filter, and then tune them. So that'll be good. Now the problem here is I don't know what. Well, sorry, we've got two issues. One, we know that we need to output 5-volt signals for the main board coming from a 3.3 volt device. Problem number one. So we need to scale that 3.3 volt voltage. Well, first we need to filter it into an analog voltage. Then we need to scale it to 5 volts. So we can either filter first, scale second, or scale first, filter second. It's not going to matter too much which way we do it, but what I would prefer to do, is filter first, and then we can feed into a scaling sort of, some sort of scaling block, and then we can output a nice low impedance signal to the board. Did you get Nick's backpack? Great. Okay. So let's just wifey off to work. So, we can probably use like a Salink here, like a Butterworth filter type thing for that. So topology is going to be something like, filter, scale. So we're going to need to go from 3.3 volts to 5 volts. We only have a 5 volt supply on board, right? Which means that we either need, because with the easiest way to do this is going to be to feed the input into an op amp and provide some sort of controlled gain so that it scales pretty much exactly from 3.3 volts to 5 volts. And then maybe some, some tuning on board, because that voltage, you can see it was not exactly 5 volts, it was like 5.2 volts. So I'm not sure if that's just, it deliberately runs slightly higher voltage and it's expecting 5 volts as the range, or whether we do need to go right up to that 5.2 volts to avoid losing resolution. So some sort of trimmer would probably be ideal, I'd say. So problem being, coming back to that a lot of op amps aren't rail-to-rail op amps, which means they can't actually output a signal or handle signals right up to their supply rail. They have kind of like an upper and a lower limit. So rather than going between 0 and 5 volts, they might be able to amplify off, power between 0 and 5 volts. They might be able to operate between signal swings of 0.5 volts to 4.2 volts, maybe. It's fairly typical. You can get rail-to-rail op amps, but you have to make sure specifically that they are rail-to-rail. Now, we could solve this if we had like a 9-volt input. We could just power our op amps off 9 volts, and then away we go. Just gain up to a 5-volt output, but adding the extra circuitry to sort of charge pump or a like a boost converter up to a higher voltage just to power these op amps, it's going to be a bit of a pain when we could just choose a rail-to-rail option. So we need to take a look. I'm actually not too familiar with rail-to-rail op amps. I don't do a lot that requires them, because if I'm doing audio design, I'm using really nice high analog rails anyway, so I don't need to go right up to those. But actually, I believe in the, let me go back to this screen here. I've got to cut away because I need to look up some, I'm going to reference a FlexiHub schematic, and that's not released yet. So that is not quite for your eyes yet. And it's not going to be an open source product, but not quite ready to show off everything about that yet. But I believe I was using, had a similar-ish application. And I was using some rail-to-rail op amps, and they were, what are they? The 324Z. Right. Pretty common op amp. But if I'm using them for something else, I'd like to use them for this as well. Beautiful. Just always a 4-channel quad op amp, rail-to-rail. And it can have supply voltage up to 5.5 volts. That's going to be pretty much perfect for our application. Love that. And if it is slightly over 5 volts, it's going to give us a little bit of extra headroom. So that's great. Big fan of that. Big fan. Okay, well, cutting back here to our control board. Let's close that pane. You didn't see that. Haha. Under this ICs, maybe I brought it in for a Fusion library. I'm going to be using an LMV324. I just went past it, didn't I? Here we go. Great, we've got a rail-to-rail op amp ready to go. There's that quad op amp package. So what we're going to want to do is have a design just one of these and then duplicate it. Let's take a look at some topologies. We could just use like a 2-pole low-pass filter, like a passive filter, and just run it through our op amp, or we're going to take a look at some different filter topologies. So I haven't I wish I had a whiteboard or something. I could draw these out and explain them. I might just have to rely on some Google searches. Saline key filter, very common second-order filter. It uses an op amp. You get a response looking like this. It's going to be very nice. You can do high pass, low pass, band pass with it. So that's our voltage divider. I'm not going to go through and derive the maths. I think that would be a little too dry, even by this stream's standards. RC filter circuit. I'm trying to find just a regular schematic to show you to reference. This is high pass. No, we want low pass because we want to filter out. We've got a PWM signal that's switching really quickly, right? We want to filter out those changes and just have a nice, smooth analog voltage. And the faster we can run our PWM at, obviously has its own challenges to handle with fast switching edges, but it means that we can use a higher kind of cutoff frequency so that we don't have any limitations in how quickly the pots will respond and still have a really nice ripple-free option. High pass. I'm just trying to find if they have a schematic for a low pass option. so that I can kind of walk you through how the circuit works. They're all high-pass filters. Okay. Just want to find a nice schematic. Here we go. So here's our schematic for our low-pass filter. Now we're going to make a couple of assumptions. One, to simplify the design. Both of these resistors are going to be the same value. Both of our capacitors are going to be the same value. So we're going to have the same like cutoff point for both poles of our filter, so that we just get a nice deeper, so 40 dB roll off. So let's make this, 1K for, you've got to start somewhere, right? We'll make this 10 nanofarads. Got to start somewhere. We get a frequency of 15 kilohertz, which is going to be way too high, but we get this really nice steep roll off compared to like a passive single pole filter. It's going to give us much better attenuation. So we probably want that to be in the order of, increase it by an order of magnitude. Let's say we're going to want, we don't really want to use 10. Let's use 100 nanofarad capacitors if we can. That's probably going to be pretty good cutoff frequency. Maybe we're going to want some 5K1 resistors for our USB-C, CC1 and CC2 pins. I know, oops. Sorry, 5.1K. That should give us a cutoff frequency of about 312 hertz. It's probably going to look pretty good, I think. Yeah, I think that might look pretty good. Great. Quite like that. Yeah, it's going to look pretty good. So this is how our basic like two-pole active filter works. It's just called a Salem key filter topology. You can get, as I said, low pass, high pass, band pass configurations, however you might want to do it. We can sim it in Spice if we like, but there's not really any need. We know that this is going to work pretty well. So let's go back to our main screen here. Going to borrow these 100 nanofarad capacitors here, and we want one to be there. In fact, we might sim it because I think it's going to be a fun exercise. We can look at what the voltage ranges are. We can really kind of tweak some gain, because this is going to be a unity gain amplifier. Going back to our schematic here, you can see we've got this negative feedback here connecting our output directly to the inverting input of our op amp. And so that is going to provide unity gain, which is not what we want. We want to provide non-unity gain. We want to step up from 3.3 volts to 5 volts or 5.2. And we want to be able to have some control over that. So maybe a trim pot is going to be required, I'd say. Okay. What I might do is bring up some LT Spice simulators so that we can see what's going on. And it's also, hopefully, a bit of an interesting exercise into using LT Spice. I'm going to create, hang on. What on earth am I looking for? Okay. What I'm going to do is create you've got a new schematic, and LT Spice has a user interface that is just abhorrent, but op amps. We're just going to want the universal op amp model, universal op amp 2. Actually, I think the particular one I'm after, because I'm not, unless it has, it's not going to have the exact part that we're using. I don't think. I don't think it will. If it does, I'll be very happy. But no, it's not going to have an LM324. That doesn't matter. We're not after the actual performance characteristics of said op amp. We just want to get an idea of our gain and what kind of values we might want to be looking at for that. Op amps. Op amps. Spice. All right, universal op amp it is. We are going to, how do you mirror in Spice? Tools. Spice makes it very hard. There we go, it's E. Right, E. Move. Spirits control E. Yeah, there it is. And then control R to rotate. There we go. Okay, so we've got an op amp. Then we're going to want some capacitors. So putting one there, one here, and oh, where did we go? Come on, Spice, you can do it. And some resistors. I need to skew this. So we'll look back at what our schematic looks like, so we can remind ourselves. So this is what we're aiming for. Okay, so we're going to draw this schematic along with some power and everything else in Spice. Let's switch back to that main screen for a second. Okay, that to there. Now I'm going to make some connections to here. I told you Spice was painful, but it is a really nice tool for simming. It's just the user interface leaves a lot to be desired, for sure. Pretty much just has never changed. Cool, then we're going to need to add our negative feedback there. It's looking pretty good. We'll add our ground reference for that capacitor. Cool, so that's the basic building block of our schematic. Let's move that out a bit. Oh, geez. There we go. Cool, now we're going to want some power. So, in fact, we'll just compare back so you can verify that everything's looking good. This is what our LT Spice looks like. And this is what our reference looks like. It's looking pretty good. So, power. Component. Voltage. So this is going to be the DC voltage supply. So I'm not sure I put it all the way down there, but anyway, let's bring it up here a bit. And we're going to add a net there. Let's call it plus 5 volts. There. I'm going to put it on our op amp. Oh, it's mirrored that, hasn't it? That's frustrating because everything's going to look upside down. Anyway, and then we're going to put a test voltage in, a test signal. Then we're going to look at our output. So, component. I'm going to be relying on, I'll probably go back and forwards between, Google some resources because I don't have a drawing pad to draw out the schematics I'm after, and it's going to be so much quicker to just do a Google search of what it is I'm trying to explain and demonstrate than to draw it by hand, as you can see. So, all right, now we want another voltage source here. Going to just zooms out when I'm trying to. Oh, come on, there we go. Around there. So just got a DC voltage here to power our op amp. And then this, let's go to advanced. We want to set up a pulse waveform, okay, because we're going to make a square wave that we're going to filter. Now, you notice there's no frequency here. Okay, so what we need to do is use our frequencies, calculate the on and the off times, so we can set our duty cycle based on that. All right, so bring up the calculator. What do we say our PWM can run at? 7.5 hertz to 125 megahertz. Let's run it at 100 kilohertz. So the slower the better, because then we don't have as much EMI considerations and really fast edges, but also we want it to be fast. Let's just go with 100 kilohertz for now. So pulse, there's our calculator. So if we know that the period of a waveform is equal to the inverse of the frequency. So frequency, so 1 divided by 100 kilohertz, so 100,000. Hang on. 1 divided by 100,000. 0.001. And so if we convert this to a more useful term, if that was a 1 there, this is the way I think that would be 1 millisecond. So that is 100 microseconds, 10 microseconds. Okay, so is one full cycle, and let's go with a 50% waveform. So we want that to be half of that, so 25. Sorry, no, we don't want a rising edge. We'll go T on 25, and our period is going to be 50. So now we can adjust this T on to set the duty cycle. We'll make it initially start at 0, and our V on can be 5. Don't need any delay. Don't want to bother setting the rise times, anything like that. That's going to do just fine. Ooh, let's move this away so it's a bit less cluttered. Okay. Now what we want to do is set, we're going to do a transient analysis. So we're going to look at the response over time. And to do that, we can go add a spice directive. Yeah. There's a nicer way to do this, like with a GUI. So there we go. Yeah, we just go edit simulation command. So transient analysis stop time, we'll do this for, I don't know, 10 milliseconds. Too long. Set X. We don't want to, wait for the supplies to power on or anything like that. Yes, I know I haven't put any values in. All right, so this resistor, what do we say? Our low pass filter, we're going to use 5.1 kilo ohm resistance. 5.1K for both of them. So it's sort of 5.1K and 100 nanofarad, and we'll see how this performs. It's going to be so much quicker and easier to do once it's set up than building it from scratch. This is obviously messy and hard to follow, but it's just a prototype, quick and dirty simulation, so we don't really need it to look too fancy, but I'll clean it up a little bit. Okay, and then our directive. So if we run this, what didn't you like? Unknown V. Oh, yes, of course, it didn't like, it won't like me saying. Oh, hang on, what did not like there? Does not like my label name? I don't parameter V. Oh, okay, so it doesn't like that voltage on there. Cool. So we can see we've got our supply voltage, 5 volts, in our transient analysis up to 10 milliseconds. We've got our input signal, which has not been generated. Ah, because this needs to be in, what do we say, microseconds. There we go. All right, so we're going to make our simulation time a bit shorter, I think. Maybe 1 millisecond. It's better. That's reasonable. We've got it from 0 to 5 volts. But actually, we want this to be to 3.3 volts, because that's what our Raspberry Pi RP2040 is going to output. There we go. You can see it's just approximated some slew rates for our rise and fall time, and we can look at our output. So the capacitors take a little bit of time to charge because they're averaging this, all right? So, if we made the cutoff frequency a lot higher, we wouldn't quite have this problem. So what we might do is change our simulation to be over 10 milliseconds. See, rises up to is fairly stable. It's rising, fairly stable value. We've got a little bit of ripple here. All right, so let's get our cursor and look at it. Ripples, zoom in on a snapshot here. It's sitting at about 1.8 volts, which is about what we expected, given that we, it's about half it's about half. But I think what we want that to be is period and 4. A little confused as to why it's averaging that to why it should be 1.6 volts. Why is it 1.74? If we've got a half, unless I've just absolutely smooth-brained something here. Like if we get our cursor on here, it's going right to 3.3 volts. Yeah, that makes sense. Let's delete. Oh, how do you do? Anyway, okay, so that is a little bit interesting. I honestly, it's been a morning. So why are we getting 1.74 volts? We should have no additional gain. Let's take a look at what's happening after our first polar filtering. We are going to delete this trace. We don't really need to see our supply voltage. And what I'm going to do is wait for this to stabilize. So we're going to go time to start saving data. Let's go 9 milliseconds. So we're just going to look at a much smaller period in time. Simulate this. There we go. So let's delete that trace. Here is our filtered signal. A little bit of ripple, but it's doing a pretty good job of attenuating that roll off, which is quite nice. Okay, so I would have thought if we make that, I'm pretty sure I've just stuffed something up here, like 1 or 0. Well, let's make that 50. That's going to be essentially full on time, and yeah, that's going to go up to where's my okay. Let's just simulate that to our output. Yeah, that's what you'd expect. And when it's half, it should be. Let's make it a quarter. Duty cycle. What's green now? Oh, green's our output voltage. Right. Where's our? Something funky's going on. Where's our input waveform? Let's just delete these traces because I might have, been viewing the wrong trace. Our pulse. T on T. Oh, oops. The old milliseconds instead of microseconds trick. That'll get you. So here's our waveform. That's looking good, and our output should be here. So if we look at what half of 3.3 volts is going to be 1.65 volts, and then half of that again should be 825 millivolts, which is a little bit higher than what we're getting. I think I've stuffed up just something on the duty cycle calculations. If that's we're going to go up to, going to increase the frequency a bit, so it's a bit easier to sort of visualize what's going on. All right, cool. To be honest with you, I am just a little uncertain as to why. The other thing is I'm just using a universal op-amp model here, so but it should be giving me it should be giving me a 0 gain output. It must be something to do with these duty cycle settings here. Try. So that should be giving me. Might do is get rid of the period and make it. That's stuffing something up. Just make the. Oh, and I can't do the off time, can I? really brief pulse. Okay, so that should be 1% in theory, and it's a little bit less than. Less than 1%. I'm just trying to work out why that's not exactly accurate. This is the sort of stuff that I just sit using about, trying to work out exactly what's going on. All right, so 10% of this is right, because 1% of 3.3 volts is going to be 33 millivolts, right? And we can see here that we've got this, pretty much the average of our output is 3.265, 70. It's going to be, some sort of drop due to those resistors. But if we go, so what is it? 3.2657 plus 0.3, we get, rounding up pretty much 3.3 volts. I wonder if it might be actually just some nonlinearities with our resistance. The cutoff frequency isn't going to affect things too much. We get a little bit of extra ripple, but what we might do is just bump the capacitor values up to move that, and we get, that's looking nice. All right, now let's make that don't want that red trace anymore. Is the blue trace our output? I'm not 100% sure. Yeah, it is. So that is 1. Oh, okay. I'm not sure what the characteristics of this op amp is with it's just a universal model. So, it's looking close enough. That really should be, ideally we want that to be nice and linear. So, if we use some lower impedance kind of components, or I'll show you what happens. So 50% duty cycle here, right? Neglecting any rise and fall times. Although that does not look even. I think that might be what's going on, because that duration, right? Let's delete this trace. So we're just going to be looking at here. Now let's just snapshot just very small part of the waveform here. Here we go. Now, what's this time? Oh, no. Cursor, thank you. What's that time there? Just going to look at, the sort of some of the timings here. So 60. Bing, why? No, calculator. It's literally there. Don't search the web. I just want the calculator. So 60.08. Where's my second cursor? There. 60.08. So 60. So it's 40 microseconds of high. And then is it 40 microseconds of low with, a symmetric kind of rise and fall? No. Okay, so it's you can see it's low there for 154 microseconds, and then from 105. So it's about 50 microseconds of our low, then 40 microseconds of our high. So I think we might just manually need to go into this pulse and set. We'll make it nice and fast, just like a 1 microsecond rise and fall. So it's symmetric, and that should look a bit, there we go. That looks a bit more symmetric. So let's go and look at the timings. Yes, you cursor, follow me. All right, number 2 there. Where's number 1? Here. What's that? 40. Okay, so 47 thereabouts. And then obviously it's not going to be perfectly accurate when I'm just dragging the cursors around. 47 and 40 there and a bit. It's looking a lot more symmetric there. So if we look at our output again at a supposed 50% duty cycle, we should get, yeah, 1.61 volts. So we just had to make sure that our duty cycle was nice and symmetric. So that was just my oversight. I thought maybe this op-amp model had some sort of, I don't know. Anyway, there we go. Nice filtered output. Beautiful, beautiful. We can take our input frequency even higher, and it's obviously going to do a better job of attenuating that. But let me delete all the. Let's just get rid of that. That to me. Sorry. Oh, that was just real zoomed in and showing. Okay, so that we can see the output ripple here. So we can see our total ripple. We use some measurement here. Goes from what's that? 1.61 volts, right through to. Okay, so there's a total ripple of 0.004 volts. All right. I'm pretty happy with that because that's 4 millivolts of ripple. That's basically going to be less than supply noise ripple. I think that performance is quite adequate, even at just at 100 kilohertz, which we can, of course, drive a little bit higher. For example, if we... in fact, this is less than. This is at 10 kilohertz, I believe. What is... so 100, 1 divided by 100. Yeah, so this is actually 10 kilohertz. So, even if we were to run it a lot slower, we'd still get quite adequate performance out of that. So we can play around with these values a little bit. The actual like frequency response of our filter can be really easily tweaked. That's not of a concern. What we want to do is get the gain staging. Get the gain staging of everything. Let me just rotate that capacitor. It's like, why is do so? Anyway, okay, Spice. Play by your rules. All right, give me 1 second, folks. Sorry about that, folks. All the viewers. I just had to go get some Neuro for my heads. Ugh. Bit of a headache. Anyway, so now we've got our filtered output. We get a fairly sinusoidal, it's not actually sinusoidal, but roughly sinusoidal response. Well, it's not perfectly sinusoidal. So now we need to look at our gain because we need to gain up our signal from 3.3 volts to 5 volts. And what I am imagining is, yeah, what I'm imagining is that, I wonder if we could somehow, okay, I've got an idea. Instead of using some gain in the op amp to kind of scale up our signal, and because the issue is we basically want that the max level to be exactly whatever the supply voltage is, so that the it's as accurate as possible going back to the control board. Now, instead of doing gaining it up with our op amp for gaining the analog voltage, what we could do is essentially just use a level shifter straight off our PWM signal, right? To give us, and if we're using a level shifter, it will shift it to exactly that supply voltage if we construct it properly, and then we can run that into our op amp filter, which I'm liking that. I'm liking that a lot more. So let's move all of this this way. Okay, now if you're not sure kind of what I'm talking about with level shifters, let's go back to, say, drawing the schematic out again. I'm going to go spark fun. Very, very common circuit. This is basically a very well-trodden path. So this is a spark fun part, and it's a bidirectional logic level converter. We don't necessarily need it to be bidirectional. All we're going to do is create a buffer, some sort of like FET-based buffer. Now, it's going to be easy. Like I said, it's going to be easier just to show you, what's going on a pre-existing schematic here. All right. So, in fact, this isn't the best example. I've got a specific circuit in mind that I'll use, and rather than drawing it out, I want to show you a cleaner looking schematic first, and then we can kind of talk about it and discuss it. So, what are we going to want to do? Yes, we want something like, no, I don't want current drivers. I just want a to be honest. Yeah, anyway, a couple of different topologies. I don't really need it to be bidirectional as part of the issue. Not at all, but this is pretty much what we're going for, because we can use one less resistor here. All right. So I'm going to be using a MOSFET as a switch and just driving it into to saturation, so to speak. So this will be an interesting Hackaday article. Blah 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 blah. So it's talking about CMOS to TTL. So 5 volts to 3.3 volts, and so on and so forth. All right. Now this is basically what we want to do. Okay. And is going to invert it. So we'll have to keep that in mind, but not really the end of the world. Now, of course, we don't want it to be bidirectional at all. We don't care about that. Okay. All right. Let's look at some MOSFETs. So, I was trying to see if they had a better schematic, but alas, they don't. What we're going to use is what's they? NMOS. There we go. All right, I'm going to put this in here. I'm going to delete this trace. Okay. So that's going to go to ground. It's going to look a little something like this. What's the copy? Huh? I'm just getting your resistor here. Place that there. My 5 volt. Copy. There we go. It's one of the function keys. So none of them are assigned to sensible macros. Just going to take a tap out from there. There we go. And touch the end of this. Yeah, I am not surprised that people are tuned out because this is kind of dry, but hopefully if you're watching this and you want to do these sort of simulations on LT Spice, it'll be interesting too. Okay, so, and as well, you know, just for the sake of having my resistors the same value, doesn't really matter too much. Let's get rid of that. To run our simulation, we're going to look at a signal here, 3.3 volt square wave. Look at our signal here. Oh, that's pre-filtering, of course. Ah, okay, yeah. That's what we might need to do. Ah, sorry, wrong way. Let's make that like a weaker pull-up because it's just destroying our filtering, isn't it? I'll show you the operation of this. Hang on. Let me delete that one there for a moment, just because the idea is I'm look just at this signal here. Okay, so you can see this is kind of working okay, all right, but not ideal. So I'm not actually sure what the threshold voltage this MOSFET is. Might need a much just a generic MOSFET model. So it's really not liking that, is it? Might add a gate resistor to get some faster turn off. But at that point, you know, we defeat the purpose. We're going to have to use 2 resistors, depending, you know, rather than looking for a really low gate threshold. So in other words, sorry, I need to clarify. Gate threshold is the threshold voltage that the gate of this MOSFET is going to sort of fully saturate, because we want to slam it, right? Just drive it into full saturation. But this particular model might have a lower threshold voltage, so this isn't really going to help, but it's going to illustrate the purposes of using like a pull-down resistor on the gate of the MOSFET while we're here looking at you know, designs. Make it 100. See, yeah. Even just adding a gate there, pull-down resistor isn't going to affect anything. All that's going to be doing, this is driving it. So this is useless. You would use that when you just had like a single-ended output to drive this MOSFET. So rather than, what are the characteristics? I mean, we can pick a new MOSFET. I don't want to spend too much time just going into the depths of looking at different MOSFET models. This is very, very dry viewing. Sure, let's pick that MOSFET. You can see, watch the, you know, kind of the characteristic change bit. So depending on what MOSFET you pick is really going to affect the actual performance of things, right? So that's why it's very important to make sure that you're actually using the right model. So what we might do instead is just sort of take the, you know, the more tried and tested logic shifter approach. Let me take a look. For this, I'm going to want to use like a BSS. I know a BSS 138, something that I've used in some designs for a lot of stuff. It's been tried and tested to death. Sure, 1, 2, 3 or 1, 4, 5 is going to do the job. So give me the videos. Can't be bothered to go through and calculate the VGS from these things. Use one. Let's just look up the data sheet for it. So what's that? That's a BSS 123 from Fairchild. Okay. All right, you know, this will do the job. I'm going to whack that in there, and we're going to go to like a you know, just a more of a typical logic level converter topology, which means we are going to just get rid of some of this. All right, now rotate. I want to find a resistor, so I'm just sort of speeding through this a bit rather than, you know, finding a reference schematic and this and that, so I can get through what it is, you know, just putting this together a little bit quicker. Hang on. Do F9. so we can actually get to something a bit more interesting. Yeah, so starting to drag out a little bit, but this is the reality of a lot of this kind of work. You just tinkering around with things, seeing what's going to work for your particular application. But once you start doing this, you can kind of not rush through, but rush through these designs a little bit more. All right, we want that to be high side. Want that to be there, and then we're probably also going to need to make 3.3 volts. Why? Here, I should say. Go ahead and copy that over to our low side. There we go. I think it's going to be about right. This up. Oh, connect this up. All right. Let's now delete these traces because they could be different nets. I'm going to take a look at this over time. Lovely, 3.3 volts. And here's our 5 volt trace. So you can see it smooths these edges out a little bit because if you're familiar with how a MOSFET works, there's actually some internal capacitance here. And so combined with that 10K resistor is going to, filter those sharp edges a little bit. And you can see that if we make this 1K, that's not really pronounced enough to show much of a change. Yeah, there you go. You can see if we make those 1K, it's a lot steeper, but it's obviously going to use more power, and we're going to get, not as ideal. But we can take advantage of this because when we're looking at the performance and the EMI characteristics of our board, my goodness, this stream has gone on a while. I'm on a roll. I'm in the zone, even if no one's watching. I want to get watching live. I want to kind of just keep pushing on with this. We can use this to our advantage by, using that internal gate capacitance and our RC network here to filter out some of those sharp changes, so that we get a little bit better performance out of our filter. We don't have those really sharp edges propagating through to the rest of our board. So 10K is going to be pretty good value for just softening out those edges and just rounding them off a little bit. Okay. And now we bring a little bit, we'll connect this up to the rest of our circuit. The beauty of this is it's going to be a lot less a lot less finicky about the exact MOSFET that we choose, as opposed to, just trying to go for like a more simple unidirectional model before. We could do it the way that I was going to do it, or rather than, there's a lot of different ways to do that translator if we're using the MOSFET as a switch, but then you have to bias it properly, and not too difficult, but beyond the scope of this stream. So here's our input. Why is our input? That's been attenuated. Oh no, there we go. Just must have been a different trace. And our output. Okay, yeah, we're going to have some sort of some impedance issues going on here. So for the sake of pick those back up. No, they really need to be a lot lower than these resistors is part of the problem. So make these 51K so we can get them a good order of magnitude beyond voltage divider here. There we go. So, all right. In fact, if we make those 5.1K, then we should still get some of that nice filtering roll off on those edges there. Yeah. Still a bit too close for comfort, and we're getting some voltage divider sort of effect in there. Whereas now, if we look at that, yeah, that's pretty much 5 volts. Not quite 5 volts, but pretty much. And we could, of course, lower those and squeeze more performance out of it, but not really that necessary. For example, if we bump these up to 100K, higher and higher, because these resistors are essentially forming a potential divider. We're getting attenuation there. I would really like to use that as a filter. It's not critical though. Now we see our output. Let's take a look. The whole point of this. So it should be exactly more or less, there you go, half of our supply voltage, which is 5 volts. And we can see it is let's get a cursor on here. 2.455 volts. So slightly lower, and we do have some losses coming in here. So what we're going to do is just reduce the overall impedances going on here by some orders of magnitude. And you can see we get reduced ripple effectiveness. Sorry, reduced attenuation of those ripples. So we need to bump our capacitors up a bit. Now you can see it's actually a little bit higher there. So that, right on a ripple. There you go, 2.56 volts. So now we're actually kind of going the opposite way, and they're biased a little bit too far. A lot of this is just, making sure that we don't have this interaction. We could, of course, use a separate buffer circuit here, but we want to avoid that. We're just going to set our values so that we have, limited kind of interaction here. So you see, now that that's much higher, this pull-up resistor is in fact not being a pull-up resistor, but kind of introducing a DC offset into our signal, which really isn't ideal. So we need to make sure that these are, fairly well matched. You can see the effect of what's happening here. So got a nice 5 volt output. That's good. But these resistor values really are too 5.1K is same. All right, so that's looking pretty good. Let's get rid of that. Don't know why I just got rid of that, but you can see here we've got our output nets. We've got some issues. For sure. So if we make this significantly higher impedance, like 1 meg, look at how changing the effect of this, see, because that pull-up resistor just dwarfs the input impedance here, and so it's really going to reduce the effectiveness of our circuit, which is part of the issue. So it's really going to be a case of just sort of fine-tuning some of these components here. And you could calculate this and actually go through and do it by hand. It's honestly a lot easier just to do what we're doing now and kind of guess and check when it isn't performance critical, I find. What we're aiming for is we want our output to be right on that 2.5 volts, and then we can look at the performance of the rest of the circuit as we sweep that duty cycle. So change the one there. So bumping these up a little bit, I get it to that 2.5 volt mark. So it's a little bit too much. So we're trying to just find the sweet spot where the pull-up resistor there. So again, pretty close, where the pull-up resistor is kind of fairly well matched to the impedance of this network here. So look, that's pretty good. This is a learning exercise. I'm showing you guys how you would go about sort of simulating some of this. But the issue now is that because our pull-up resistors are a bit lower, we don't have this full full range here. So it's introducing a bit of DC offset, but this isn't ideal. So even though it looks like it's performing well here, you can see it's not actually, because it is introducing some DC offset, which is why it looks like it's pretty much on 2.5 volts. But we're going to get, if we make this, this should be, it's going inverted, it should be a bit higher than that. But because we are introducing that, it's not going to be spot on performance wise. And in fact, let's make this like basically 0. So 1 should be up there, but it's not. You can see that's because we've got some impedance issues going on here. So going back to our 25 microseconds. So what can we do? What can we do about this? It's an interesting use case. Well, one, we can buffer the output of our logic shifter here, but this is starting to get to the point where it's like, we add another buffer and it's really just, we might as well not be bothering with this, okay? There is another solution that doesn't, rely on having to have this, because part of the issue is the output impedance here is causing some issues. We want this to be driven with a really nice low impedance input, but then when we lower the impedance, we get some issues. So what are we going to do? Get rid of our voltage divider. Get rid of this. Instead, what we're going to use is another op-amp. And you might be saying, what, another op-amp? I thought the idea was to simplify things, and it will. It will. I promise. We want to copy that. So we got that there. There. Hang on a second. Okay, so let's take a look at what this is going to do, but we don't want to go to 5 volts. Instead, actually, I don't know what I was thinking. I had a, sorry, my brain's absolutely cooked. I was thinking we wanted to go the other direction and step it down, down from there. Anyway, so we've got, let me just do that because I was trying to illustrate a point and then realized that there was no point doing it that way. So you can see we've got these kind of performance trade-offs with using this kind of topology, so a digital level shifter going into our Salem key filter. Okay, so a couple of options we have is to make this, if we make this a lower impedance, then it's going to, hey Michael, how you doing? You're on the tail end of some dry LT Spice simulation. We're just looking at CD catching up. We've got our design and fusion, which is coming together nicely. We've got our ADC, our microcontroller kind of core with accompanying flash programming connectors, and our pots. And we're looking at whether we can use the built-in PWM channels of the RP2040 instead of a dedicated DAC. But part of the issue is, which I didn't expect, this was, hence why I'm not super prepared for this, and it's taking a while to come up with a nice solution, is the Deco actually is 5 volts on the control board. So everything's done using 5-volt logic. Now, the RP2040 is going to be running at 3.3 volts. So we're going to need to convert those analog voltages. And I want to make this design as easy to repurpose as possible. So using the PWM channels, they can run nice and fast. We're going to be looking at the best way to scale that output, because this would be easy if we knew it was guaranteed like a rock stable 5 volts, but it's actually about 5.2 volts on the board. And part of my worry is that if we tune it to sort of go from 3.3 volts to exactly 5 volts, you would think it was 3.3 volts, but not to be. I don't know if it's maybe the new ones are, but yeah, these pots all swing from 0 to 5 volts, 5.2 volts actually. And I'm a bit worried that if we just aim for 5 volts, that we're going to lose some range in kind of the upper end of the pot suite, which isn't ideal. But I'm also worried that perhaps it is 5.2 volts. I'm not sure what tolerance of the voltage regulator is, because if I had 100 units to test and they're all like 5.24, 5.25 volts, then cool, let's use that as our gospel value. But I don't want to tune it to output a little bit, gain it up to more than 5 volts on our supply, and then we start getting some clipping on the if we just were to use some feedback get some gain in on this op amp stage, because then we'd get some non-linearities in the clipping. So my thinking is it might be better to translate the 3.3 volt PWM signal into our 5 volt signal. I'm just thinking about doing this in a way that's easy enough for people to follow along and doesn't reduce, you know, a whole bunch of external circuitry to get high performance, because then we might as well just use a cheap DAC, right? But it's a good, I think it's a really interesting learning exercise in how we can kind of translate these, you know, these lower and step up the 3.3 volt PWM signal. Now, part of the issue is if we use like a bidirectional converter design like this, then we're going to get these impedance issues. So what we might instead look at is just using something like a BJT, I think is going to be, because it's a current-driven device, is going to be a bit more reliable because our GPIO pin is certainly going to output enough current to really drive a BJT into saturation. So that's the background. The catch-up going to take NPN. All right. Let me just move there. Okay. Now, a couple of different kind of topologies we can do. We'll put a small resistor across the base here just to avoid. Just make that like 100. Yeah, I honestly was really surprised. I would have probably wouldn't have put any money, but in theory, I would have put a lot of money, proverbial money, on it being a 3.3 volt control board, or even lower, maybe like even down to a 2 point something, probably not a 1.8 volt, but given it's, I would assume it's this DSP, you know, going to have some GPIO, and I would have thought it would just be running at a much lower voltage, but apparently not. Anyway, resistor here. 2 years. Yeah, they are somewhat older pedals, but, you know, and I brought that point up that this particular microcontroller, like I think it was released in 20, you know, if it's the same one used in the Blue Sky, it was released back in 2011 or something like that. And if it's the same chip, then this chip would have been designed in the 2000s, probably, you know, mid to late 2000s. And 3.3 volt logic was just certainly not as common then, which that doesn't seem that long ago, which is kind of crazy. So anyway, is what it is. We going to, so this is just doing a bit of fun trial and error of just showing like different kind of topologies for translating our 3.3 volt signal into 5 volts and seeing some of the different trade-offs and you know, trade-offs and limitations of the different topologies. So delete these traces. And let's take a look at what happens. Now, so we'll run our simulation. Here's our 3.3 volt input signal. Let's take it back to 50%. Oh, my keyboard's been just ghost 50% duty cycle. There we go. And I'm actually just going to increase the fall times so they rise and fall times, so it's just a little bit more of a clean square wave. It obviously won't be that fast in reality, but yeah, be easy to see what's going on. All right, so you can see here that, again, we have some of the other issues if we just whack, you know, a high value resistor there. And without going through the maths of what's happening, this resistor, all right, so let's step through this. So, you know, it's a current-driven device, but essentially when this goes to 3.3 volts, it's going to be turning this transistor on. We're going to make a couple of assumptions that we'll drop that, you know, that down to like 1 ohm, so we can negate any losses there. So, assuming that we get a nice amount of current, you know, slamming this transistor on. Okay, so we've got our VBE, which is our base emitter. Kind of voltage is going to be 0.7 volts, let's assume over there. Anyway, it's going to allow current to pass through here, which is, essentially going to pull this here right down to 0 volts, which you can see is what's happening. That's exactly what's happening. And then when it turns off, this resistor is in charge of pulling it back up to what should be 5 volts. Except that, I'm not explaining this to you, by the way, Michael, you know all this, but if people who are interested, except that we've got this 51K resistor here and this 20K resistor here. So we're running into some of the same issues we had with our previous design, where we've got this attenuation of our 5 volt signal. What might we do about this, you say? Well, we can reduce this to 10K. See, that's better. That's looking a bit better. Now, but it's still not quite all the way there. So let's make this 1K. Getting close, getting close. So we can go 100 ohms. Really sucking back the power here. Okay, so now we've got this really good looking square wave. Okay, let's take a look at our output voltage. So it's still a bit low because we're going to get, it's not going exactly to 0 volts there. So a few reasons. It's, what is that? Should be 2.5 volts in theory, exactly. And that's the goal, but it's 2.4 volts. All right, but we can see that this kind of configuration is working a lot nicer to translate our 3.3 volt signal to a 5 volt signal. And it is inverting it. That's important to keep in mind. So we could go like a non-inverting configuration and tap off the emitter here, horses for courses. But we wouldn't get quite as good a performance, but then it wouldn't invert it. What we're doing here, but it doesn't go quite to 0 volts because there's always going to be some voltage drop and some losses through this transistor here. So you can see that is going not to 0 volts, but it's going to 18 millivolts. And all of those, that's going to add up to not quite being 2.5 volts. So let's go back to our original configuration for this. Not our original configuration where we had 51K. See how that's going to impact our performance. So you see here, now we start having some real issues where the impact of this resistor is sort of, really dwarfing the rest of our circuit here. So it's pretty clear that we can't make this too low. So if we make it 5.1K, we start going back, the opposite direction. So I think for the sake of simplicity with this type of circuit, it's going to be a bit of a trade-off. 50 milliamps, yeah, exactly. So that is part of the issue. If we look at when this transistor is on, let's just assume that this is a short circuit and that there's no kind of, no voltage drop across any of the transistor, which is, of course, not the case. But we know that I is equal to V on R. So if we have 5 divided by 100, then that's going to be 50 milliamps being pulled through there, which is just a colossal amount of current to be drawn, and it's probably going to be, it's not going to exceed this transistor, but it's way more than we're going to want. All right, so this is another trade-off of doing it sort of in this way. So it gives us better performance in some cases, but imagine if this, this is going to be an average current, so it's going to be sort of alternating between 0 milliamps or thereabouts to whatever the base current is, to 50 milliamps. Averaged out, still 25 milliamps. What if this is all the way on as our duty cycle increases? Well, that's just constant 50 milliamp draw. We have 5 pots. That's a quarter of an amp just for our digital to analog conversion, which is not good. Definitely not ideal. So I'm actually, we obviously can't use this kind of topology. It was a bit of a learning exercise as much as anything. I am a little bit, not stumped, but I just need to think about the best way to do this, because part of the issue is I really want to make sure that we get the full range out of our pots, and I don't want to just assume 5 volts is the kind of the max, because it could be designed to be running at say 5.2 volts for all I know. I haven't looked exactly into what's going on this chip and where that regulation is coming from, but I want to assume that it needs to output the max of that supply voltage. But we you know, we don't know whether that's how much variance there is in that supply voltage. So yeah, like I think that a FET-based, you know, logic level converter is probably going to be the better option, but then I don't want to have to add another one just to buffer these PWM channels. Like by the time we get, you know, even though this is a quad op amp that we can use and it is rail to rail, and we've got the quad op amp, we've got two, let's say two FETs. If we add another buffer in between each stage, it's just going to start getting a little bit complex in terms of our component count. We could just sort of bypass this, and rather than using dedicated MOSFETs, we could use like, you know, an actual sort of like buffer driver or something like that. You know, we could look at, I've shown you before. Let's take a look at what would happen if we went for a slightly different topology. The whole point of this and why I'm sort of laboring through some of this is it's really fun to learn. It's really fun to learn, you know, some of this stuff and follow along if you're not used to it. And it can just be the sort of thing that I think is sort of interesting, looking at these design trade-offs of different topologies. And so it's worth just exploring all our different options, which has been the point of this as a learning exercise, right? So now we're going to be tapping in this as like a, sorry, I'm trying to make this a bit neater, but I'm not doing a good job at making it any neater, I don't think. Here's our 5 volts. So I'm going to tap here off the emitter. Okay. Now let's take a look. I'm pretty sure our net names will have changed, so let's just delete those for simplicity's sake. All right, so there's our, that shouldn't be our input. There we go. It's like, why is that happening? Let's look at our output. Okay. So again, this value is way too low because having the opposite issue where, okay, so you can see part of the issue going on here in that these resistors, these really need to be typing on the keyboard a bit larger. You know, we're starting to get some better performance, but it's really not going to play nicely, especially if we were to reduce these to like 1Ks. It's just not a great design going into, you know, this sort of impedance network here. If we want to use this style of, or this topology for filtering, I should say, and I don't want to use analog gain in our op amp for fear of, you know, if there are some differences in the supply voltage there, and then we start running into clipping and non-linearities. I really don't want that to be the case either. So let me just think of the best way to tackle this problem. Because this could be kind of solved easy with just a dedicated DAC or an extra, you know, buffer or something like that. And what I mean by that is we could just go, sorry, I'm just having a brain moment. Okay, I guess we could, you know, maybe use like some P-channel MOSFETs instead, and then actually not be a bad option. We could use like BJTs instead of just MOSFETs. Could be a good option. Honestly, I'm really just not 100% sure on the best way to tackle this problem. I need to just think about it a little bit. Again, it's that supply voltage that's just causing me to be a bit cautious because I do want this to be as easy to repurpose as possible. Is part of the conundrum, I guess. You know, we could use another op amp to buffer our square wave output. That would be a good option. Then we'd get, you know, pretty high performance. That would actually be a pretty high performance solution. So I'll show you what I'm talking about if we did this. Right now, actually, I'm going to undo and go back to our previous. All right, so we're going to go back to our what's called a common emitter amplifier. There's not really so much an amplifier as it is a buffer here. So honestly, I want to try and make this a little bit more power efficient if possible. So look at this in isolation. Going to add a resistor for our load. Okay, and this is what our just our kind of converter is going to look like. I'll make this, you know, 1 meg load. These signals are what we want to be looking at. Here's our input, 3 volt wave, and here's our output, a 5 volt wave. So, you know, we can make that like 1K, and then it's still 5 milliamps per channel, which I don't love, but it is quite nice and fast. Yeah, it is kind of tricky to do it. Like level translation is easy to do. It's, you know, logic level shifters are cheap and cheerful. If you're caring about digital signals, the tricky thing is that I'm trying to avoid any voltage drops where possible because our digital signal is going to get fed into an analog signal or converted into our analog signal, and I don't want to do any gain staging on this op amp because I want it to rely on kind of slamming into that quote unquote 5 volt rail so that it's always going to sort of threshold between whatever that supply voltage is, so we get a full sweep going to our chip. And I'm just trying to work out a nice one cost effective, but 2, you know, somewhat easy enough to understand for people. If this is going to be an open source project, I don't want to be using weird esoteric parts or kind of, you know, convoluted designs or anything like that. So I still don't want to be dropping 5 milliamps per NPN on there. So I am wondering if going back to a logic level switch there might not be the best option. What I'm going to do is take this out and kind of leave it intact, right? And this is why I was doing it like this before. So it's all the way, you know, here. I'm going to bring our logic level shifter kind of MOSFET based topology back here. Oh, Spice, why are you like this? Okay, there we go. Now we'll make those 10K. You can see. See what this is actually a really interesting design problem. I kind of didn't properly anticipate that, you know, quote unquote, the complexity of this as a design challenge until I really thought through and I measured the fact that was not 3.3 volts really just threw me for a bit of a spin because it does have a significant impact on how our design is going to look. So, you know, here we go. This I think is going to be the best bet because 1, we get a really nice right to 5 volts level translation, but we also can take advantage, like I said, of that gate capacitance and, you know, so the internal capacitances to the MOSFET package to add some additional filtering on the edges of those, you know, just filter out those really sharp transitions to improve our EMI performance a little bit. 5.1, I think that's still pretty quick edge, but it just rolls off that sharp corner a bit. So that's nice. Now, what I was talking about before in terms of buffering is now we have the issue of we can't just choose any old components we like for our filter. And that's part of the problem. We want to get good performance out of our filter. We want, as fast a response as possible while filtering out all that noise. And if we have to make these resistors a certain value, then we can't just use our common, like 100 nanofarad capacitor values that we want, and it's going to add the cost and complexity of the project. So here's what I think we might do. We're going to use an op-amp buffer because it means if we wanted to do add like another buffer here, then we're going to run into the same issue. And we can get a quad package op-amp. Like that's not much of a problem. And I want to overbuild this design a little bit in terms of having extra channels in the topology to use for future designs. So let's go ahead, copy this guy here. We're going to use this, as a buffer. All right, because this is a rail-to-rail op-amp that we're going to use. Essentially, it's going to tap onto this. So now let's take a look. So our simulation still got that, and out of here, get a perfect, more or less perfect mirroring, but we don't have to worry about the impedance of our logic level converter, and we can tie off nicely to here. And this buffer is basically isolating these two stages. So, we run it again and it's exactly the same. And our output, smack bang on 5 volts, ignoring some of that little ripply bits. That's a thing of beauty. I was trying to avoid, having to add a second buffer stage, but I think for the sake of just a really high performance thing, and why you might say, well, just add, an 8-channel DAC in and away you go. The problem is, what if said 8-channel DAC goes out of stock? This is what designing in post-COVID chip shortage times looks like. If said 8-channel DAC goes out of stock, we're sunk. We kind of can't really get away from it with the ADC, but we can pretty easily decouple ourselves from those sort of supply issues because resistors, some capacitors, we can change op-amps. Rail-to-rail op-amps are going to be available, and Jelly Bean N-channel FETs are going to be available. This design is going to be, I really hope I don't put the mocker on myself, it's going to be fairly shortage proof. I'll always be able to get these parts to make this design, and that's also part of the goal. I didn't talk about it too much, but we get a really nice high performance design. I actually can't remember how to step through the duty cycle of the off time, because I wouldn't mind actually varying that time dynamically and seeing the response, seeing how well it tracks. Stepping duty cycle pulse. I haven't used Spice for dynamic kind of simulations like this for ages. I just cannot remember the best way to just create like a sweeping PWM signal in Spice. I know there's like a whole bunch of ways you can do it, but if I can actually just bit of a screen in a second. I'm just having a look. Pulse train, that's exactly what I want to do. No, I don't want to like build a pulse width modulator and then run a signal into it. This is meant to be a quick and dirty simulation, and that's going to be sort of beyond the scope of what I'm trying to do. That's not even LT Spice, that's Spectrum Soft. Yeah, all right, I'm going to have to set up like an actual kind of pulse generator. Don't want to be doing that. But yeah, hopefully, now that is going to be a nice topology for our circuit. I'm kind of just going to keep doing this. This is probably going to turn into a 4-hour stream because I really want to sort of smash this out and get this into the schematic. so that for next week we can go ahead with some board layout and things like that. So this is what it's going to look like. These are kind of the key elements. I'm using 5.1K pull-ups here and also 5.1K resistors here because they are going to be common to other parts of the schematic. I'm going to need to use those for our USB-C connector anyway. So we're only using like 1, 2, 3, 4 unique components, and they're not even unique because they're going to be for other parts. So it's really just a MOSFET and some op amps, which is good. Now let's come back into here. Here's going to be our data conversion section. So I'm just going to pull this Spice window up so I can double check the component values here. All right, let's go ahead and create our Salem key filter. And this whole thing could certainly be avoided using other filter topologies. I'm not saying that just a basic Salem key filter like this is the be all and end all of filter design. It's certainly not. But in terms of low component count, pretty good performance and basic topology and component requirements, we don't have to worry too much about component tolerances or anything like that. This is it's a pretty good filter. Pretty good filter for this purpose. I need a resistor. And because, I think it is important, especially in the current part shortage, that if I'm designing this with the intention from the get-go of being open source so that people can build their own, it is really important to consider things like component availability, not just from, say like LCSC or MAUs or something like that. DC sweep simulation tab and simulation setup. Yes, you do. Cool. But I don't believe you can directly sweep the duty cycle from that. I could be wrong. Like we can do our DC sweep. But then I'd just have to build like a pulse, add a comparator and some extra bits in. And this is turning into a mammoth stream anyway. I don't want to waste too much more time on, simulating, because I know this is gonna work pretty well. And even if the performance, does need to be tweaked, that's just going to be adjusting some values of our Salem key filter. There we can pretty easily, we could go to 10K or down to 1K if we need to increase or decrease the frequency, cut off by anything significant. So. All right, so here's our filter. It's looking good. It's looking good. Just pinch it in a little bit. Cool. Now we need our buffer. So we're going to invoke the other gate of this as our buffer. I actually am going to swap those. If for nothing else, then I am just super nitpicky and I would like, yes, that's fine. And I would like A to come before B. That's the kind of person I am. All right, so I'm just going to add our buffer stage, tidy up those bits. Thank you to Fusion for being nice and slow and unresponsive while I'm trying to get the move command going. I really appreciate your work. All right. Lovely. We'll probably just add, I will just add a very small capacitor in there, probably to just help reject any radio, like RF interference or things like that. Feedback loops quite easily. I'll just put a 220p. There, and also just, if nothing else, add a little bit of extra filtering, which definitely can't hurt. So cool. Move all this over a bit, and we want our MOSFET. What values do I have? I remember if in Fusion I have a separate FET library. I don't think so. I just put it all into a transistor library. All right, I've got a BSS 84. I can't remember exactly what. So these are all. You can see there's various NPN, PNP transistors here. We've got some JFETs thrown in there as well. It's the mix. Blah 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 blah. I'm just going to try and find some nice common ones. So that's P channel, not ideal. Oh, that's like a big power one. Whatever, we're just going to use a generic MOSFET. Give me a second. I'll go away. All right, where did my let's go. Oh no, that is an N-channel MOSFET. Sorry, I just can't see it very well. Okay, let's put that. I'm just going to double check that particular part. It's not some solve. Oh no, I can't. Oh yeah, it's too small for. Not even too small for my eyes. I don't even have old man eyes. I'm just silly. Whatever. We use this. I'll find an exact part to use later on. It's interesting that that symbol's backwards. Like that's a P channel symbol, if I'm not mistaken. It says P channel FET, and the other one was an N channel FET symbol. Does this just have the wrong symbol on it? Maybe. Knows. Well, use a BS 250, I suppose. See if there's a surface power. No. Yeah, we're just going to use our schematic. This symbol is an N channel, so works for me. And I'll replace it with a suitable part. I'm not sure what some of the common N channels that we use on manufacturing here. I'll have to double check. Let's go up to there. Okay, now there's our 3.3 volt power. Yes, and 5 volt power. All right. What are you up to today, Michael? You got much on for the rest of the day? That's looking nice. Yeah, it's looking all right. Unless I'm confusing the way that that's drawn. No, anyway, I know that needs to be N channel. And then that's going to come from our PWM channel. So, call that PWM 0, I guess. Kids nails to bed, same for you. Yeah, it'd be nighttime over there for you, I would imagine. I hope you had a good day at work, mate. Just obviously kind of getting the workday going here, but this is looking pretty good. So that's going to be one channel of our analog to digital, our digital to analog converter. Essentially, it's going to be fairly, again, knock on wood, fairly chip shortage proof. It's going to be, quite robust and give us good performance, good tracking over the range of frequencies that we want, and doesn't use any sort of really niche parts or things like that. So then we can finish up at a label on there. call that like back out 0. So that's pretty much it, folks. That's what goes into, you know, converting our PWM into an analog voltage out. And there were definitely some tricky design criteria. We'll give it a save for good measure. Definitely some tricky design criteria that took a little bit of thought, you know, going into it. And if we look at our PCB layout here, we can see it's starting to get pretty chunky. A lot of components coming in here. It's going to be a fairly packed layout, but nothing too crazy. And next week, I'm going to sort of go ahead in preparation for the stream and duplicate some of those sections. We can get into the PCB layout side of things and finishing up on our mechanical design. So if we finally, I'll show you so you can get an idea of the component relative component sizes. This is just our dummy control board. Those components are just sort of placed roughly close to where they'll need to be, close to the pots. Wait for this to render. And yeah, so there's our RP2040. Got this big train of chips there. That 3D model's kind of rotated on its side. That's not ideal. I'll have to fix that. You know, we've got our op amp, our ADC chip, some buttons, and all the rest. So that'll be it for now, guys. That was a almost 3.5 hour stream. This is meant to be an hour and a half stream. I got a little bit carried away because there's plenty to do. I'm off to get some Bridge 4s ready to ship out, along with some gizmos, do some app testing, some editor testing, and I'll see you guys next week for another Teardown Tuesday. Take care. Wait, now I've got to